Hi everyone, welcome to another practice problem walkthrough with physacademy.com. In this video, we'll learn how to use the conservation of energy law to calculate a proton's speed as it accelerates through an electric field. Then, we'll calculate how an applied magnetic field will bend this moving proton's trajectory to a circular-shaped path. Let's read and analyze the problem together. In an experiment, we wish to find how many hydrogen atoms in a gas have their electrons ionized, in other words, removed. Alright, let's take a second here. The term hydrogen atoms that don't have their electrons literally means they are just a simple proton. They are accelerated through a 4.5 megavolts potential and fired in the positive x direction towards a magnetic field of magnitude 0.045 Tesla. The magnetic field points out of the screen toward you in the positive z direction. The magnetic field region starts from x equals 0 and ends at x equals 1 meters. Okay, so this is a two-stage problem. In the first stage, we give the proton some speed using the electric field, then in the second stage, protons go through the magnetic field and, therefore, their trajectory turns to a uniform circular motion sort of a path. Part A. Calculate the y component of an ionized hydrogen atom's momentum as they leave the magnetic field. Part B. Find the angle, alpha, between the initial velocity vector of the ionized hydrogen's atom's beam and the final velocity vector after the beam emerges from the field. Ignore relativistic effects if you know what I'm talking about. Part C. Why would the trajectory differ for a non-ionized hydrogen atom? What would be that trajectory? Focusing on parts A and B. Let's analyze the story of this problem and see step by step what we need to do. I start with analyzing state 2, where the protons come out of the magnetic field. At this state, protons make an angle of alpha with respect to the positive direction of the x-axis. We are asked to find the momentum of these protons, and this angle, alpha. Momentum is the multiplication of the mass of proton times its velocity. So, we need to find the y component of the velocity first. Also, we know sine of alpha is the y component of the velocity divided by the magnitude of the velocity or speed. In addition, we know that a magnetic field doesn't change the speed of a charged particle. Actually, it only changes its velocity direction, and the magnitude of the velocity remains the same. So, because at states 1 and 2, speeds are the same, if we find the velocity of the protons at state 1, where they are about to enter the magnetic field, we can use that value for state 2 as well. Now, about alpha. As these protons enter the magnetic field, they go through a UCM. If we assume the radius of this circular path is r, we can say the sine of alpha is delta x divided by r. So if we calculate r, then, from there, we can find out the numerical value of alpha. Alright, now that we have a roadmap, let's find the speed of the protons as they get to the magnetic field at state 1. I'm going to use the conservation of energy law. At state 0, the kinetic energy is 0 because the speed of protons is 0. In other words, they are at rest. But they do have an electric potential energy because the potential electric field in this region acts on the charged particles. Anyhow, using the conservation of energy law, we get the following expression for speed at state 1, which is the same as the speed at state 2, as we discussed earlier. After plugging in the numerical values, we get a huge number for the speed. It is alright because protons are so light and small that they'll move very fast as soon as we apply an electric field to them. Now that we have the speed, we can focus on the second stage, where the protons go through the magnetic field. Setting the magnetic forces equation equal to the UCM equation, we get the following expression of r, the radius of the circle. Then, we plug in the numerical values and get about 6.815 meters for the radius. Let's analyze this result for a second before we move on. As you see, this radius is larger than the width of the region of a magnetic field, or 1 meter. Because of this, we know for sure these protons come out of the right edge of the field rather than the bottom edge. Alright, now that we have the speed and the radius, we can go back to our original equation and calculate alpha, which is 8.438 degrees. And then using this angle to find the y component of the velocity. Then multiply this velocity by mass to get the momentum of the protons. After some numerical calculation, we get 7.2 times 10 to the power of negative 21 kilograms times meters per second. Let me really quick summarize our answer for parts A and B. For part C, when particles don't have an electric charge, first of all, the electric potential couldn't push them to start moving in the first place. Even if we assume somehow they were already moving, the magnetic field cannot bend their path, and they'll go straight through without sensing any magnetic field. This is it. We found all of the variables we were asked to. Thank you very much for watching this video. Please check our website, physacademy.com, or our YouTube channel for more practice problems. If you found it helpful, please consider subscribing to our YouTube channel to support our work.